Institute of Space Studies, Dr. James Hansen, who's probably the most well-known and respected prominent US climate scientist, in the last month has released a paper. They've concluded a 30 million year marine sediment study looking at the history of climate going back 30 million years. So prior to this they had, the modelling was largely generated on computer simulation and ice core data. Now they've got a track record looking at deep ocean sediments going back 30 million years, and they've concluded that if we stabilise at the current target of 450, if we look at the fossil record, every time we hit 450 and hold at that level, we actually deglaciate the planet entirely. So we lose East Antarctica, the Greenland ice cap, all the ice on the planet, and basically we foment a 75 metre sea level rise. So he's saying that is clearly not the target we need to be looking at. It's really around 350 or below to bring the planet back to the climate back to safe thresholds. He's also, and I must add, quite optimistic that we can actually ramp to as close to zero emissions economy as possible, and we can actually sink carbon debt quite efficiently using some of the emerging technologies that we're seeing come to light. So, what's a safe climate look like? Well, this is the level prior to the Industrial Revolution, 280 parts per million by volume. We had an atmospheric carbon load of around 596 billion tonnes of carbon floating in the atmosphere at that time. According to this breaking science, we passed that safe threshold of 350 parts per million around 1990 when human-sourced carbon emissions drove the atmospheric carbon level to around 745 billion tonnes. At the moment, we're at 2007, we're at 820 billion tonnes of carbon, we're at 385 parts per million. It's ramping up a couple of points each year. And if you look at what's happening, I'm not particularly happy with what's happening to the planet at the moment. I don't know how many people in the audience are, but I'm not particularly happy to see what's happening to the Murray-Darling Basin at the moment. Food shortages, acidification of the ocean, all the major ecosystem changes that are ramping at the moment. Then if we look at the targets of stabilisation at 450 parts per million, I'd suggest that we actually need to have a really good look at recalibrating targets in accordance with the science that's emerging. And we also need to recognise that we've got about 100 billion tonnes of surplus carbon floating in the atmosphere that we need to deal with and sink into forests and soils and potentially the ocean if we're going to pull atmospheric carbon levels back to 350 parts per million. So what's required? Well, we need to ramp to a near zero emissions global economy, and we also need to draw down carbon debt. So we need to actually be thinking with global carbon markets. We need to create a carbon debt market which actually recognises that carbon debt, recognises we've got that 100 billion tonnes of carbon we need to deal with, and allocate that to the historical emitters, which is predominantly the developed world, and apportion that responsibility. I'll talk a bit more about that. So, moving to a zero economy on the left and dealing with the debt. So on the right, dealing with the debt, we need to capture that released greenhouse gas. And again, as you'll find in the NASA science, they're pointing to soils and forests as the biggest leg up to assist us in that process. On the left, moving to a zero economy, prevent the release of greenhouse gas, move to a decarbonised energy infrastructure and energy efficiency. How do you do it? Well, as we've been talking about, a massive energy efficiency drive, and then a rollout on a very large scale of quite proven and also emerging zero emission or renewable energy technologies. So sorts of things we're seeing. We're actually seeing major movements of very large levels of venture capital into new and emerging solar technology at the moment. So here's a concentrating heliostat solar farm in Spain. The smaller one on the top of the screen was built in 2006. This one was built in 2007. Basically arrays of mirrors that are concentrating solar onto a tower which then produces steam for electricity production. Here's a 1 kilometre by 1 kilometre one that exists in Nevada at the moment. It's a parabolic trough solar concentrator, quite simple technology. We're seeing the emergence of some massive multi-billion-dollar projects in the US at the moment. Here's a very simple one developed by an Australian scientist, David Mills, AUSRA. He didn't have a favourable investment climate here, particularly under the Howard government. He's now moved to the US and he's been picked up by venture capitalists, including Google, and they're rolling out this particular very simple system on a very large scale in the US at the moment. We've also got Keith Lovegrove, the head of solar thermal at the Australian National University. He was in today's Herald Sun. We'll have to talk to the Age about why they didn't pick that one up before the Herald Sun did. But he's talking about that they've just actually poured the foundation blocks for the largest baseload solar plant that's been built, I think, in the world here. So that if you read today's Herald Sun in the business section, you'll pick up that example. He also presented recently, and this is a neat little slide that he's highlighted, which shows the amount of area using his technology that it would take to actually produce all of Australia's energy needs. And if you look at the little box, 138 kilometres, you'll see that 20% of that's actually covered with the collectors. 80% of it allows co-cropping or co-agricultural use. So, of course, you'd actually spread that strategically, a whole lot of those sort of arrays strategically around in strategic positions to feed into the grids. We've also seen a breakthrough in the last 2 weeks in terms of baseload wind power, compressed air storage using limestone caverns, where when you've got peak wind production and it's not meeting peak energy demand, you can actually store compressed air and then re-release it to drive turbines to produce power. So we've got these opportunities to use the grid and all these technologies to produce baseload, which is the major important catch cry for energy reliability and security. Other sorts of things we need to look at are electrification of passenger transport. So fly-by-rail, ultra-fast rail to displace aviation emissions, which are a major vector of greenhouse gas emissions globally. Plug-in hybrids are another one. So there's modelling that shows that 80% of commuter vehicles could be done within the battery range of plug-in hybrids that can run on full renewable energy, which charges the batteries. The other one is, of course, using this abundant renewable energy we're all carrying on our waistline nowadays. These battery packs and getting out, walking and cycling, becoming a cycling culture. Of course, there's another one. Electrify city commuting. These are wireless trams in Bordeaux. They don't have overhead a power source, very similar to the ones we have here. And electrification of cargo trams. So this is Volkswagen. This is how Volkswagen moves their freight in Germany through electrified cargo transport, and of course electrified long-haul freight driven by renewable energy. Of course, we need to look at zero carbon houses. The UK's identified a target of making it building a zero carbon standard by 2016. We're looking to do it in 2009 with 200 houses with that Eco Village project we were talking about. Upgrading existing houses to 7-star, and also looking at the carbon emissions from commercial buildings as well. Now this is the interesting one that we were talking about, biochar, sinking carbon into soils, dealing with carbon debt. This is a soil profile in a place in the Amazon basin. Amazonian Indians have used this technology for thousands and thousands of years, and basically they burn the crop residue in a low oxygen environment. Using that technology, it basically produces a carbon-rich char. So a lot of the charcoal or the carbon is stored in the char, and that char was then spread back across their croplands as a natural fertiliser. They were doing it to build up their soils and the fertility of their soils. They had very poor soils. Using that technique, they built up these massive carbon-rich soils and sunk billions of tonnes of carbon, and these biochar soils, or terra preta soils as they're called, cover 10% of the Amazon basin. Very ancient technique, building soil fertility, but it's actually a massive carbon sink. We're seeing soil scientists now revisiting and relearning a lot of this old science, and this is something that could be used to sink massive volumes of carbon on marginal agricultural land and generate another revenue for farmers on marginal agricultural land. So you see the biochar soil on the left,